And then the very last topic is how to do DFTs how to plot it using MATLAB. So the magical command for it is freqz. Unfortunately, it only works if you already know what the DTFT is. So you still have to compute it by hand. Let me give you an example of how to do this. Let's say you want to plot the DTFT of this signal. You can use freqz. In order to do that, you'd first generate your omega variable. In MATLAB, we don't have omega, so I'll use W. And I'll plot it between 0 and pi. And then my DTFT is equal to this freqz command of the numerator values, the denominator values. Let's say this is minus 3 j omega, so we're going to have, this is minus 1 j omega, minus 2 j omega, and that will be the minus 3 j omega coefficient. And we'll feed it in our omega values. And this is truly just the same thing as if I wanted to do it by hand and said it's equal to 2 plus 3 times complex exponent of minus j times omega divided by 1 minus 6 times the exponent of minus 3 times j times omega. So this and this is the same way as doing this. It's just, this just gives us a shortcut. It's not much help. And then the final thing is to plot it. So you get that. Or if you want to find the energy density spectrum, plot of your omega, and then the absolute of x dot raised to 2. That's our whole class. Any questions about any of this?
For the syntax and the second command you have there, could you explain again what the 2 zeros in between the 1 and the negative 6 are?
Sure. If the bottom looks like this, then that would correspond to A, B, C, D. So in the particular example that's given, we don't have any e to the minus j omegas or e to the minus 2 omegas. And so in a particular example we have, this would be equal to 1 minus 6 e to the minus j 3 omega. So this would be a 0 and a 0. Make sense?
Yes, sir. Thank you.
Sure. Actually, I should have said that would keep it in the same format. All right. I know that this stuff, DTFTs, what you should see is that the DTFTs kind of intuitively make sense here. You can see where the energy is versus omega. I want you to see that the DTFTs are continuous in omega, even though they're a Fourier transform of a discrete time signal. But even though that they're very intuitive, I hope you can see they're also very difficult to work with. They have a certain theoretic beauty, but they're abstract, and they're MATLAB can't even compute it. The most MATLAB can do is just simply plot it if you've already figured it out by hand. We're going to fix all that. We're going to fix that with the DFT as opposed to the DTFT and the next several lessons. And that will make life much, much simpler on one hand, but trying to connect what the DFT is to the DTFT requires you to first feel comfortable with what the DTFT intuitively is representing.
Sir, a quick question. When we're doing the energy density spectrum, you pointed out on the graph where the highest energies is, but I was writing down, so I didn't notice where you pointed that out.
Oh, sure. So the highest energies would be where there are peaks.
Thank you, sir.
So at the corresponding omegas where there are peaks. Here's why it's actually interesting. You're a young engineer who's just been hired for Dominion Electric. They need to do routine maintenance on their generators. And their generators, they need to do maintenance on them because they're massive multi-ton units. They've got these big bearings on them. If those bearings did wear out, you'd have this multi-ton thing spinning 60 times a second that would break the bearing containers and would start rolling around the floor. They want to stop to do bearing maintenance, but they only want to stop to do bearing maintenance when they need to. They don't want to have to stop every couple of days and check, because to take a generator offline is a big thing and it puts a lot of stress on the remaining generators. So how could you practically tell if a bearing is about to fail? Well, you could listen to it. You could put a speaker up next to it, and that speaker would give you data. You'd sample that data, and you'd end up having X from your speaker. And if you sampled it at, say, 44,100 times a second, which is a standard audio sampling rate, you'd have a bunch of numbers. And you'd be generating more numbers at a rate of 44,100 times every second, because that's your sampling rate. If there's no bearing failure, then you would expect to see the distribution of energy in that signal to be low and to be fairly uniform. But if there was something wrong with the shaft, it developed an imperfection in it, and it was causing a bump every time it went around that bearing that was causing the bearing to wear, then every time that bump hit the bearing 60 times a second, there'd be a sound that would be coming off of it. And then because we have these reflections in the frequency domain, the DTFT domain, you'd see continued reflections every rotated around that pi. There we go, something like that. And also on the left. And so if you saw a DTFT that looked like that, you'd say, what is this frequency occurring? Where is that frequency occurring? And if it occurred at a discrete time frequency that corresponded to the continuous time frequency of 60 hertz, you'd say, we've got an impending bearing failure. We got to stop that machine and fix it.